Hi everybody, welcome back to the channel. In this video we're going to be taking a look at antiderivatives, which you can probably guess is going to be talking about working through derivatives backwards, which is exactly what it is. Now this is a little bit tricky because we've been talking about a lot of different ways to find derivatives throughout the semester, including a lot of different rules that can be hard to keep straight. And so there are a lot of different rules as far as antiderivatives as well. Now I will say this, we're not going to take a look at every different kind of antiderivative that we're going to see in this semester. We're going to leave some of that for Calc 2 when you get to Calc 2 class, but we can at least start out by looking at some of the more basic functions and be able to understand how do you undo some of those basic functions. So let's take a look at an example. Let's say that we have something like this. F of x equals, we'll start out pretty basic. How about 4x to the third? Okay, and if you want to find the derivative of that, you know what the derivative looks like. It looks like 12x squared. So let's say we kind of start out working this problem backwards. So what if we start out with a function that looks like f prime of x equals 12x squared? And I said, what does f have to look like? Could you work backwards and think about this? Now, I know you can because we just had that on the previous page here. You know exactly what this should look like. But let's think about how could we walk through undoing a power rule, okay? When you have a power rule, the idea is we need to deal with the exponent as either going down or going up, depending on which direction you're going, okay? When we're taking a derivative, obviously you're dropping the power by 1. So when we think about undoing that and kind of undoing the power rule and working from f prime back to f, we're actually going to need to make sure that our exponent goes back up by 1. All right, so let me give you kind of a structure to think about a power rule. Here's how I would approach this, and you'll see me write this a lot in this way. I would start out, if you know what f prime looks like and you're trying to find f, start out by writing the constant out in front, or I shouldn't call it a constant, but the coefficient out in front. So go ahead and put that 12 out in front. And then what we want to think about is what does the exponent need to be on the original function f if f prime had an exponent of 2. Okay, so remember when you're taking an antiderivative here, you're undoing that product rule. So the exponent shouldn't go down by 1, it should go up by 1. So we need an x to the power of 3 up there. Okay. Now, if you think about how the power rule would work, if you start out with this f of x, the 3 would drop down in front. And so somehow what you need is you need a way to be able to cancel that 3 dropping down in front to leave you with a 12 out in front as your coefficient. And so whatever your exponent is now that you've gone up by a power of 1, I'm going to just go ahead and put that fraction that undoes that power out in front there. So if you have an exponent of 3, I'm going to put a 1/3 to cancel out that 3 dropping down. So now, if you were to take the derivative of this, you would have that 3 drop down. 3 times 1/3 is 1. Those just cancel each other out. You still get that 12 out in front there. Okay, but then we can always simplify our answer here. And 12 times the 1/3 that we have in front is 4x to the third. Okay, but we didn't just jump right to 4x to the third. You might be able to do that with some practice. I'm going to write it as the coefficient out front, then deal with the exponent, and then put some fraction out in front that's going to cancel that exponent dropping down. By the way, you can always check your work. If this is supposed to be f of x, how do you find f prime of x? Well, you know how to do that. Go ahead and just do that. And finding the derivative of 4x to the third, does that give you the 12x squared that you started with? Yes, it does. So you can always check your antiderivative work by taking the derivative of your end result and seeing, is that what you had at the beginning that you started with? Okay, let's take a look at another example that's a little bit more complicated, but still using a power rule. Let's say I give you one like this. F prime of x looks like 2x to the 7th plus 4x to the 3/2. Okay, and this is f prime of x, so what we want to know is what does f of x look like? Okay, so again, I'm going to kind of structure this in the same way. When you're dealing with the 2x to the 7th part, by the way, you can handle this term by term just like we did when we were taking derivatives. You can take an antiderivative of each of these terms separately and then just add the result. So really not anything new there. But when you take the antiderivative of 2x to the 7th, I'm going to leave the 2 out front. And then what should happen in the exponent? Remember that when we're taking an antiderivative for a power rule, the derivative should go back up by 1. So we should have an x to the 8th. Now somehow I need a fraction that's going to cancel that 8 dropping down in front. So I'm going to put a 1/8 there. And so in our simplified version of f of x, it's actually going to end up looking like 1/4 x to the 8th there for that first part. Now let's look at the second part. Again, I'm going to kind of follow the same structure. I'm going to write a 4 out front. Now think for a second, what should the exponent be when I'm taking an antiderivative going back up? Remember, we got to add 1. So we have 3 over 2 and then add 1 in the exponent. That gives you 5 over 2 because you're really adding 2 over 2. Now I need to have some fraction out in front that's going to cancel that exponent dropping down. Well, the exponent that would drop down with the power rule is a 5 over 2. So I need a fraction here that's going to cancel out the 5 over 2. It's always going to look like the reciprocal of that fraction up in the exponent. So if a 5 over 2 drops down, the 5 over 2 times the 2 over 5 that I put here are going to cancel each other out, and you're just going to be left with that 4 out in front. Now you can simplify this a little bit and combine your coefficients together out in front here, and you get something like 8 over 5 x to the 5 over 2. Okay, how do you check your work? Well, take the derivative of what you get at the end, and what you should get for your derivative looks exactly like at the very beginning, what we called f prime. So let's just check it. So check. When we take the derivative here, f prime should look like, let's see, 1/4 times 8 times x to the 7th. There's your power rule. And then over here it should look like 8 over 5 times 5 over 2 that drops down. And then you drop by a power of 1 when you're taking the derivative, so it should look like 3 over 2. Is this what our derivative looked like? Well, the 5's here cancel, and you're left with an 8 over 2, which gives you the 4 up in your coefficient. And then the 1/4 and the 8 here combine together to give you a 2 that you had in the beginning. So yeah, this is exactly what we started with. That's just a good way to check your work. So this is how you can deal with antiderivatives using power rules. So what happens if your function looks like f of x equals e to the x? That one should be pretty straightforward. E to the x is its own derivative, and that means that e to the x is also its own antiderivative. So if you have something like f prime of x equals e to the x, well, great, the original f of x is also just going to be e to the x. Okay. What about if your derivative originally is a cosine of x? Okay. What is our original function f of x going to look like? Or another question is, what if your derivative function is a sine of x? Okay, what is your derivative, or what is your original function f of x going to look like? Okay, this is a little bit tricky because we've kind of ingrained into our minds about how to deal with sine and cosine when we're taking derivatives. Antiderivatives work the other way. I don't think we're going to have a hard time with the actual sine or cosine function. The tricky part can be in the positive or the negative. What do you get out front? So when you take the antiderivative of the cosine, you're going to get the sine of x, and not a negative sine of x like if you were taking the derivative of a cosine, but you actually just get a positive sine of x. Okay. By the way, how do you know? Check your work. What's the derivative of a sine of x? Oh yeah, a cosine of x. Okay. What about if you have your derivative as the sine of x? What you actually end up getting is a negative cosine of x. And again, check your work. If you think about a negative cosine of x, the derivative of a negative cosine of x would be a negative, but then the cosine, the derivative gives you a negative sine of x. So there you have a negative of a negative, which is why you just get a positive sine of x at the beginning. Now, in this class, we're not necessarily going to undo all of our big rules. We have stuff like product rule, quotient rule, chain rule. We are going to take a look down the road at how to undo the chain rule, but we will not in this class take a look at how to undo the product rule or the quotient rule. That's something you'll see in Calc 2. One last example of a family of functions. We've seen a power rule. We've seen how to undo an exponential and a trig function like sine and cosine. Question is, what happens if you have something like this? This should look pretty familiar to you. What if your original or your derivative function is 1 over x? Okay, what you should hopefully have in mind, another way to write this, by the way, another way that this could show up in problems is to write it as x to the negative 1. So just something to watch out for. But even though it could be written as x to the negative 1, this actually is not a power rule. Okay, it actually is a natural log. Okay, so I'm going to write it like this for a second. The natural log of x, we're going to see there's actually a little bit more to it. But you should get a natural log here because when you take the derivative of the natural log of x, you get 1 over x. Now, in this, something that's going to be a little bit unfamiliar, a little bit newer to some of you, is that it's not just the natural log of x. What ends up being the case is that you get a natural log of the absolute value of x. And we mentioned this when we were taking the derivatives a long time ago, but it's something that can be easy to forget. It does show up more when we're talking about antiderivatives than derivatives. Okay, so let's take a look at why. This is kind of the last thing we'll see here in this video. Why is it the case that when we have 1 over x as our derivative function, we need the natural log not just of x, but of the absolute value of x for f? So let's suppose that you're starting out with a function f of x, which is the natural log of the absolute value of x. And the absolute value of x is actually a piecewise function, and it's defined like this. It says the absolute value of x is equal to x if x is greater than 0. I guess technically you could say if x is greater than or equal to 0. And it's actually equal to the negative value of x if x is less than 0. And this works out pretty nicely because you might remember that the domain of the natural log function is only positive numbers, no negative numbers. So if x is greater than 0, then the way to write the natural log of the absolute value of x is that it's equal to the natural log of just x. But if x is less than 0, we can actually talk about this situation as well. And you might say, well, wait a second, I thought you can't have a natural log of a negative. And that's true, but if you take the negative and you take the absolute value of it, it becomes a positive. And so we have the natural log of a negative x inside, where this is actually more like a negative of a negative number. So you still have a positive inside of your log. So really we have an absolute or a function that's defined as a piecewise function like this. And if you look at the derivative of f, in both cases, f prime, up in that first case, f prime of x looks like just 1 over x. Really no problems there. That's the way we've always known that it works. If you take f prime of x in the bottom piece down here, you actually get 1 over a negative x, but then there's a chain rule, and you need to multiply by the derivative of the inside, and that's multiplying by a negative 1. And so you still actually end up getting, in that second case as well, you get 1 over x. So regardless of which of the two cases you're looking at, when you take the derivative of both cases, you get 1 over x. So up here, when we're talking about the antiderivative of 1 over x, we need to account for both of those cases. So we don't just get the natural log of x, we get the natural log of the absolute value of x. Okay, something to keep in mind. All right, hope you've enjoyed the video.